In this video, we're going to learn an alternate method of finding volumes obtained by rotation, and this method is called the shell method. So let's take a look at this figure that you see on page 118 of your text. So we get this figure right here by rotating the function y equals 4 minus x squared about the y-axis on the interval 0, 2. So we're trying to find the volume of this figure right here. To find this volume, we are going to use what we call the shell method, and so we're going to divide up the region into a series of concentric shells, or what we call shells. So let's put a picture on the screen here to show what we mean by these shells. So they're pictured here in the second drawing, here that is, 4 concentric, what we call cylindrical shells. They are this gray one, this greenish blue one, this darker green one, and this black one. And if you look at these 4 shells, you see that they comprise the volume of the region, but they overshoot the volume, right? There's an overshoot in here and an overshoot here, etc. And that if we were going to find the volume, we would need to have shells inside where the gray one is, so that they would cover up the whole volume. So what we're going to do next is see how to get the volume of each one of these shells. So we've removed the gray shell, and we need to find the volume of this shell. So it has a thickness associated with it, which would be delta x. It has a height associated with it, which would be the same as the height of the function f of x, and it has a circumference which we're going to determine by the formula for circumference, which is 2 pi r. So let's move to the next blackboard to see how to get that circumference and to get the volume of the shell. So we have this gray shell, and what we're going to do is cut it down the side and display it or spread it out so that it is a flat object that looks like this. So on the original shell, let's mark its radius, which is between here and here, and let's mark its height, which is f of x, which is here to here, and then of course it has this thickness delta x, which is the thickness of its side. And so we can find all of these on the new figure, but since circumference equals 2 pi r, it's going to equal 2 pi x, and the circumference around the shell is the same as what is now its width. So its width is 2 pi x, its height is f of x, and its thickness is delta x. And so the volume of this box is going to be 2 pi x, its width, times its height, times its thickness. And so to get the volume of all of these shells, what we're going to do is sum them up. So we're going to sum 2 pi x, f of x, delta x, and when we do that, So as the thickness of these shells get smaller and smaller and smaller, the delta x gets smaller and smaller and smaller, and we are summing essentially infinitely many of these, so the error goes away, the summation sign becomes an integral, the delta x becomes a dx, and we have 2 pi x f of x dx as our volume formula for finding volume using this method. If we look back at the previous figure, notice that we are finding the volume of each one of these shells by this method, and that they are much thinner than this, and as well there will be shells that will find the volume of this region inside the gray shell that we haven't represented on this figure. So let's apply this method to find the volume of this function y equals 4 minus x squared when it's revolved about the x-axis on the interval 0, 2, that is the volume of this region right here. So what we have pictured here is a cross-section of this region, and on this cross-section of this volume obtained by revolving the function y equals 4 minus x squared about the y-axis, that's the function on the interval 0, 2 revolved about the y-axis, so the curve that we're revolving about is this curve, right? And then it gives us this volume figure that we're only showing a portion of, right, the cross section of it. And we have drawn on this a representative can, I call it a can, a representative cylindrical shell that is pictured in this green shading. So the height of this shell is represented here as 4 minus x squared. The radius, as we have seen, would be the radius of the can would be, if this is any x value, the radius would be x. So this x right here is the radius, and then we apply our formula. So the formula says the volume is 2 pi x f of x, 2 pi x f of x dx, where x is the radius and 4 minus x squared is the height. That is the radius of this representative cylindrical shell, and 4 minus x squared is the height of that representative cylindrical shell. Dx is its thickness. Remember that we are going to have cylindrical shells inside this green one that we've represented. So here I've drawn one that would be inside the green one. Here's one that would be outside of it, and so we have this whole set of concentric shells which will determine the volume of this region. If we look back to our original drawing, right, here's 4 of those concentric shells, but they're obviously much thinner than that, and they fill up the entire region. So we're just doing one shell here, and we're using the variables x that occur here. The fact that we're putting the variable x in here makes it general, as we can let x range over the set of values, which we'll see in just a minute. Now, what about the limits of integration that we want so that we get the entire volume? So if we go back to looking at a couple of these shells, one inside the one that is in the drawing and another outside it, we see that x representing the radius must be starting right, x could be a very, very small radius. We could have a can that has almost no radius. We'd have to start with the smallest can that fits inside here, and then the radii get bigger and bigger and bigger till they go all the way out to here. So the minimum radius is 0 and the maximum radius is 4. And so that's how we get our limits of integration. The minimum radius is 0, the maximum radius is 4. And we pick our radii so that we fill up the entire region. So if we continue working on this, we've got 2 pi integral 0 to 4. We distribute the x, 4x minus x cubed dx. We integrate and get 2 pi. 4x integrates to x squared, and the x squared integrates to x cubed over 3. We plug in the values 0 to 4. Excuse me, when we distribute this should have been x cubed here, and so when we integrate this we get x to the 4th over 4. And so we get 2 pi times 16. Sorry, there's another mistake I need to make. The figure goes from here to here, and so the minimum radius is r equals 0, and the maximum radius is at this x value here, r equals 2. So let me fix that. And also this should be 2x squared here. So we plug in 2 to the 2x squared and get 8. We plug in 2 to the x to the 4th over 4 and get negative 4. And so the volume is 4 times 2 pi, or 8 pi, which is about 32. Does it make sense? Well, think of it. If it were a solid box, it would have a width of 4. It would be 4 high, and it would be, 4 thick, and that would be 4 times 4 times 4, 64. But since we're just taking the circular part or the conical part inside that, its volume being about half that makes pretty good sense. So in your book, if you look at example 2 on page 119, you'll see that we get this same result, and we also find this volume using the disk method, which requires that we find the function in terms of y, because when we revolve, the radius of the disk then is a function that's horizontal. In this next example, we're going to do example 3 on page 118, where we're finding, using the shell method, a volume obtained by revolving the region between two curves about the y-axis. So in this example, we're revolving this thin sliced region, this crescent-shaped region between y equals x squared, the upper curve, and y equals x cubed, the lower curve, about the y-axis, and they intersect at 0, 0 and at 1, 1. So we're doing it on the interval 0, 1. So the setup of the problem is going to be 2 pi. The integral, the radius, is going to be as before, right here, since this is just a representative shell of many. The radius is x. Remember, there will be shells inside this, very small ones here, and then these ones out here like that, etc. Then the height is the top curve, which in this case is x squared. The bottom curve is x cubed. Remember, because x squared at 1/2 is a fourth, whereas x cubed at 1/2 is an eighth. So x cubed is the lower curve. And then the radii can be as small as 0 and as large as 1. So the radii will go between 0 and 1, and so will our limits of integration. So we distribute the x, so we're integrating x cubed minus x fourth, x to the fourth, which gives us x to the fourth over 4, minus x to the fifth over 5, evaluated between 0 and 1, so 2 pi times a fourth minus a fifth, which gives us pi over 10. And you see the additional computational details in the text on page 109. In this last part of the video, I want to do one more problem, which is problem 17 on page 123 in the exercise set. We're going to revolve the region. So this problem is different than the previous two that we've done, where because we were revolving about not about the axis, where in both cases the radius was x, but now we're revolving about the line x equals 4. So let's draw what the region between these two curves looks like first. So y equals x squared looks roughly like this, and we're only putting that portion of it in. And then y equals 4x minus x squared. I had put the function down wrong originally. So 4x minus x squared would start at 0, and it's a parabola open downward. When x is 2, it has risen to 4. So it looks like that. Now obviously the y equals x squared continues up like that, and y equals 4 minus x squared continues down like this, but we don't need that portion we just of either graph. We just want the region on 0, 2 where they intersect, or that is the on the interval 0, 2 they form a region, and we want to revolve that region about the line x equals 4. So when we do that and revolve it 180 degrees, we get this portion over here, right? So when we revolve that about, we get a figure that looks like this. So it kind of looks like a flying saucer that has this radius of 2 at the top, and this huge radius. It's completely open, and it has a radius of 4 at the bottom. So the radius, the minimum radius is 2, and the maximum radius is 4. And a representative shell is going to look like this. Right? And so that representative shell will have a radius of x and a height of the top curve, which is this, for x minus x squared, minus the bottom curve, which is x squared. So let's set up the integral. So the volume is going to be 2 pi times the integral. The radius, the radius of this is the part that is trickier to do. in all of the previous examples, the radius was just x, because we revolved the figure about the x-axis. The radius was from the axis to x, as designated by the yellow arrow there. Now, the radius of the figure is between x and the line about which it is revolved, the vertical line. So the radius is designated by that horizontal arrow, and to calculate that distance we need to subtract x from 4, right? Because this distance right here, this horizontal distance, is going to be its right x value minus its left x value. So the radius is 4 minus x. So let's put that into our formula for the volume that we're developing. So the radius is 4 minus x, and the height is, as we said before, it is the top curve 4x minus x squared minus the bottom curve, which is x squared, and then we're integrating that dx. So let's take that up on the next blackboard, and we'll fill in the missing limits of integration. So let's collect the terms under the integrand. We've got, what, 16x minus 4x squared minus 8x squared plus 2x cubed, and if we group like terms together, we'll get 16x minus 12x squared plus 2x cubed, and we're integrating that dx. Limits of integration, we said the maximum radius, remember this is the radius here, and this was the height. The maximum the radius could be, we said, was 4, and the minimum the radius could be was 2, and it takes on all values between them. So if we make our lower limit of integration 0, that gives us the maximal radius, and if we make our top limit of integration 2, that gives us the minimum radius. So here's how we set up the integral. And now let's calculate it. So 8x squared is the antiderivative of 16x, 4x cubed, the antiderivative of the 12x squared, and x to the fourth over 2, the antiderivative of the 2x cubed. Plugging in, we get 2 pi times 64 minus 4 times 8 minus 32, and 2 to the fourth over 2 would give us plus 8. Excuse me, this when we plug 2 into 8x squared, that should be 32. So it's 32 minus 32 plus 8, so 2 pi times 8, or a volume of 16 pi. So to make sure that answer makes sense, let's look back and see that we have this giant flying saucer type region, and it's these sections right here that we're revolving about, here and here, are pretty large, and remember we're rotating them about 360 degrees. So this answer of 16 pi makes good sense. So here's 3 examples of the shell method, and just one more thing on the shell method before we leave it. The shells are these here, and they overshoot the volume. They are concentric. There would be more shells inside the gray shell, and those shells get thinner and thinner and thinner, and the error gets less and less and less. And we compute the volume of each shell by cutting, or by looking at or determining what it would be by cutting it and spreading it out flat, and getting a volume of each one that looks like this, and then turning it into an integral form with the delta x turning into a dx. So that concludes this video on the cylindrical shells method of determining, or for determining, volumes of revolution.